Hi student, this is Vakumar, 11th standard mathematics, chapter number 7. In chapter number 7 we have completed matrices. Now we can discuss that new concept, determinants. To every square matrix capital A that is equal to Aij of order n, we can associate a number called the determinant of the matrix A. Look at that, a general form of a square matrix of order n. The determinant, look at that, all the elements to be written inside the two vertical lines. This one is a matrix, this is a determinant. So matrix A, this is a determinant A. Now look at the note number 1, determinants can be defined only for square matrices, not for rectangular matrices, only for the square matrices. For a square matrix A, determinant A, so what it is called, determinant, is read as determinant, is read as a determinant of A. Then third one, matrix is only a representation, whereas a determinant is a value of a matrix. Okay, so matrix, that is a structure only, but the determinant is a value of the matrix. Now, determinants of matrices of different order. Here in this chapter we are going to discuss determinant of order 1, determinant of matrix of order 2 and determinant of matrix of order 3. First one, let A that is equal to A, small a, be a matrix of order 1 because it has only one element, then the determinant of A is defined as A only, same A only. But look at the determinant of matrix of order 2. Consider the matrix capital A that is equal to, we have taken that general matrix of order 2 by 2, 2 rows, 2 columns, A11, A12, A21, A22. Then the determinant of A is defined as, write A inside the two vertical lines, that is the determinant of A. Then how to expand the determinant? You have to multiply the leading diagonal elements first, that is A11 and A22, A11 into A22. Then multiply the non-leading diagonal elements. Before that you have to introduce minus A12 or A21 into A12. Again I tell you, multiply these two, minus, then multiply these two. Okay. Here is an example. Look at that. 2, 4, minus 1, 2. The expansion is, first you have to multiply the leading diagonal elements. 2 2s are 4. Then minus 1 into 4, minus 4, but you have tried plus 4 because we have introduced minus here. This minus into minus plus 4. 4 plus 4, that is equal to 8. Okay. Now for next definition we are going to discuss that minor of a matrix. Look at that. Let A that is equal to Aij, it's a 3 by 3, be a given square matrix of order 3. The minor of an arbitrary element Aij is the determinant obtained by deleting the ith row and the jth column in which the element Aij stands. The minor of Aij is usually denoted by Mij. I tell you how it comes. For example, I consider that a 2 by 2 matrix. 2 by 2 matrix. This is a determinant actually. 2 by 2 matrix, how to find the minor of 2? Minor of 2 means for this element, leave this column and row. The element which presents the column and row should be eliminated. The which one is left out? 2. That is the minor of 2. Suppose we are asked to find out the minor of 4. The element which presents the column and row should be eliminated. Which one is left out? Minus 1. That is a minor of 4. Like that you have to find out the minor of minus 1 and 2. Minor of minus 1 is minus 1 which presents that row and column should be eliminated. Which one is left out? 4. That is a minor of minus 1. Okay. Now cofactor. The cofactor is a signed minor. The cofactor Aij is usually denoted by capital Aij. and is defined as Aij, capital Aij, that is equal to minus 1 power I plus j into Mij. Okay, for example, here it is, look at that. Compute all minors cofactors of A and hence compute determinant of A. That is one matrix. First we can find that cofactor and minor of the first element 1. You can understand? Look at that. First I am finding M11. M11 means minor of 11, the element which presents in first row, first column, that is a minor. Okay, this is M11, M12. How to find that one? M11, minor of 11. Leave this column and row. Leave this column and row. These 4 elements are left out: minus 5, 6, 5 and 2. That is the minor. Minus 5, 6, 5, 2. We have to expand the determinant. How to expand? Have to multiply the leading diagonal elements. Minus 5 into 2, that is minus 10, right, as it is. Then multiply the non-leading, then change the sign. 5, 6 are 30, 30 becomes minus 30. So minus 10, minus 30, that is minus 40. That is the minor of the first element. So minor of 1. Minor of 1. This is A11, A12, A13, A21, A22, A23, A31, A32, A33. This is A1. So minor of the first element is minus 40. Okay. Now I can go for the minor of the second element. What is the second element? You can refer the matrix. Minor of the second element is 3. Right. So for this element, leave this column and row. The element which presents the column and row should be eliminated. These 4 elements are left out: 4, 6, minus 3, 2. Look at that. 4, 6, minus 3, 2. This has to be expanded. For that you have to multiply these two. 4 2s are 8. Then multiply these two, then change the sign. Minus 3 into 6, minus 18. You have to write plus 18. 8 plus 18, that is equal to 26. 26 is the minor of the element which presents in 1 and 2, 1, 2 position. That means this is 3, this is a second element. Minor of this element, 3 is 26. Okay, like that you have to find out the minor. Now I go for that cofactor of each and every element. I already told you that cofactor is the signed minor. A11, for all the position you have to find out the cofactor. So capital A11, that is, right, minus 1 power I plus j. I plus j, I value 1, j value 1, so 1 plus 1. You know that 1 plus 1 is 2, minus 1 power 2, that is 1, into M11. M11 value, here it is, that is minus 40. So 1 into minus 40 is minus 40. Like that. Next, A12 formula, minus 1 power I plus j. I value is 1, j value is 2, into M12. Minus 1 power 3, that is equal to minus 1. M12 value, here it is, M12 value is 26. So minus 1 into 26 is minus 26. Like that, for each and every element we can find the cofactor. So the matrix has 9 elements. Now for all the 9 elements we can find the minors as well as the cofactors. You can refer this example, you can easily understand. Next definition is the properties of determinants. So many properties are there, we can discuss one by one. Property number 1, the determinant of a matrix remains unaltered if its rows are changed into columns and columns into rows. Okay. I give an example. Property 1 example. I consider a matrix A, that is 1, 2, 3 and 5. Okay. I am going to find out determinant of A. Determinant 1, 2, 3, 5. It can be simplified. It can be expanded. matrix cannot be expanded. This is a structure only. How to expand the 2 by 2 determinant? This is 2 by 2 matrix, this is 2 by 2 determinant. Very simple, you have to multiply the diagonal elements. 5 ones are 5. Then multiply the non-leading diagonal elements. After that, change the sign. 3 2s are 6, but you have tried minus 6. 5 minus 6, that is equal to minus 1. That is the value of the determinant. Now, according to the property number 1, if you interchange the rows and columns into rows, you will be getting A transpose, correct? A transpose, that is, write the first row in first column and second row in second column. I am going to find out the determinant of A transpose. So, determinant 1, 3, 2, 5, that is equal to 5 ones are 5, 2 3s are 6, become minus 6, that is equal to minus 1, same minus 1. So, that is property number 1. If we interchange rows into columns and columns into rows, the value of the determinant does not change. That is, it remains. So, property number 1 is over. Now, property number 2, if any two rows or columns of a determinant are interchanged, then the determinant changes in sign, but its absolute value remains unaltered, right? I will give an example, you can understand. Property number 2. First, I find the determinant of A. Straight away take the determinant 1, 2, 3, minus 1, 0, 1, 2, 1, 5. I expand the 3 by 3 determinant, 3 rows, 3 columns. How to expand? Listen carefully. You can expand the determinant by any one of the rows or any one of the columns. I go for the first row. Since I am considering first row, here at the top of the first row, you have to put plus, minus and plus. Alternate sign you have to. So, first I start with 1. The element which presents the column and row should be eliminated. These 4 elements are left out, that should be written in 2 by 2 minor. 0, 1, 1, 5. Next, minus 2 have to write into. The element which presents the column and row should be eliminated. These 4 elements are left out, minus 1, 1, 2, 5. Minus 1, 1, 2 and 5. Then finally, plus 3 into. The element which presents the column and row should be eliminated. We have these 4 elements, minus 1, 0, 2, 1, minus 1, 0, 2, 1. That is equal to, now you can expand the determinant 1 into, multiply these 2, you will be getting 0. Then multiply, change the sign, 1 becomes minus 1, minus 2 into, minus 1 into 5, minus 5, right as it is. 2 ones are 2, becomes minus 2. Plus 3 into, multiply these 2, minus 1 into 1 is minus 1 and 2 into 0, 0. Even if you change, you are getting 0 only. Change the sign. So, 1 into 0 minus 1 is minus 1, minus 2 into minus 5 minus 2, that is minus 7, plus 3 into 1, minus 1 minus 0, that is minus 1. That is equal to 1 into minus 1 minus 1, minus into minus plus, 2 7s are 14, plus 3 into minus 1, that is minus 3. That is equal to 14 minus 4, that is 10. That is the value of the determinant. Then, even if we expand the determinant by second row or third row or first column, second column or third column, the value of the determinant remains always 10 only for this problem. According to property number 2, if we interchange any 2 rows or any 2 columns, the value of the determinant changes only by sign. Now, consider a new determinant . Look at that. In this determinant, I am interchanging that first column and second column. That is 2 0 1 in first position, 2 0 1, and 1 minus 1 2 in second position, 1 minus 1 2 in second position, and third column write as it is, 3 1 5. So what I have done here, just have interchanged the first column and second column. I am retaining the third column as it is. Now I am going to expand the determinant. That is equal to, here also I am going to expand the determinant by first row only. At the top of the row write plus minus plus 2 into minus 1 into plus 3 into, again I tell you, 2 into minus 1 into plus 3 into. So inside that 2 by 2 minor, you have tried to leave this column and row. We have these 4 elements, minus 1, 1, 2, 5. The next one, for this element, leave this column and row. These 4 elements left out, 0, 1, 1, 5, 0, 1, 1, 5. Next, last one, 3. Leave this column and row. These 4 elements left out, 0, minus 1, 1, 2. Now I am going to expand 2 into minus 1 into plus 3 into. If we multiply, you will be getting minus 5, right, as it is here. Multiply, after that change the sign. So plus 2 becomes minus 2. Like that. Minus 1 into 0 into anything 0, 1 into 1 becomes minus 1. 2 into 0, 0, 1 into minus 1, but I have tried plus 1. I have to change the sign after multiplying the non-leading diagonal elements. That is equal to 2 into minus 5 minus 2, that is minus 7, minus 1 into 0 minus 1 is minus 1, plus 3 into 0 plus 1 is 1. That is equal to 2 into minus 7 is minus 14, minus 1 into minus 1, that is plus 1, plus 3. Look at that, finally you are getting minus 10. Previously we got that plus 10, now we have got minus 10. So that is a property number 2. If we interchange any 2 rows or any 2 columns, the value of the determinant changes only by sign. Okay, property number 2 is over. Now property number 3. If there are n interchanges of rows or columns of a matrix A, then the determinant of the resulting matrix is minus 1 power n into determinant of A. In property number 2 example, I interchange the 2 rows for only one time. So that if we replace n by 1, minus 1 power 1, that is minus 1 into determinant of A. We know the determinant of A in property 2 is 10. So minus 1 into 10, that is equal to minus 10. Look at that, minus 10. Because we interchange the rows in for only one time. Suppose we interchange the rows for 2 times, minus 1 power 2 into determinant of A. If we interchange the 2 rows or 2 columns for 3 times, minus 1 power 3 into determinant of A, like that. That is property number 3. Now property number 4, if 2 rows or 2 columns of a matrix are identical, then its determinant value is 0. I give an example. Consider the determinant. Here in this determinant, look at that first row and second row, both the rows are same. That means the 2 rows are identical. Here R1 is identical to R2. Now I am going to expand the determinant. I am going to prove the determinant value is 0. Here also I am going to expand the determinant by first row, so that you have to put plus, minus, plus at the top. Here 1 into, directly I write next minus 2 into plus 3 into. Listen, the element which presents that element 1, column and row should be eliminated. We have these 4 elements. I directly write the answer. 5 2s are 10 and 1 into 3, 3. 3 becomes minus 3. 10 minus 3. Next, minus into 2, minus 2 have written, and leave this column and row. We have these 4 elements. 5 1s are 5, 2 3s are 6, becomes minus 6. 5 minus 6. And the last one, 3, element which presents the column and row should be eliminated. If you eliminate these 4 elements left out, multiply 1 into 1, 1, and 4 becomes, 2 to 4 becomes minus 4. So 1 minus 4. Now we have to simplify. That is equal to 1 into 7 minus 2 into minus 1 plus 3 into minus 3. That is equal to 7 1s are 7, minus into minus plus 2 1s are 2, and 3 into minus 3, that is minus 9. 7 plus 2, 9 minus 9, that is equal to 0. That is a property. In a determinant, if any 2 rows or any 2 columns are identical, then the value of the determinant is 0. This is property number 4. Now property number 5. If a row or column of a matrix A is a scalar multiple of another row of the matrix A, then its determinant is 0. I will give an example. Consider this matrix, determinant 1, 2, 3, 3, 6, 9, 2 and 5. Here in that first row nothing can be taken out, no common. But in second row you can take 3 as common. If you take 3 as common, you will be getting that each and every element of second row should be divided by 3. You will be getting 1, 2 and 3. And the third row write as it is because nothing is common. Look at that. So 3 into, that is the second row is it's a scalar multiple of the first row. What's a scalar? 3 times the second row is 3 times the first row is second row. Once again, 3 times the first row is second row, correct? Because 3 into 1 is 3, 3 into 2 is 6, 3 into 3 is 9. So 3 times the first row is second row. In that case also the determinant value is 0. Look at that, right? These 3 as it is. This determinant already have written in property number 4 example, the same determinant only. Already expanded that one. What is the value here? 0, because here the 2 rows are identical. If the 2 rows are identical, the value of the determinant becomes 0. So 3 into 0, that is equal to 0. This is the property number 5 example. So what is given in the property number 5? If a row of a matrix is a scalar multiple of another row, okay, then its determinant is 0. In our example, second row is a scalar multiple of first row. 3 times the multiple of first row is the second row. Okay. So value of the determinant is 0. Now look at the note here. If all entries of a row or a column are 0, then the determinant is 0. I give an example. So look at the example. Here I am considering all the entries of the second row are 0. Now I am going to prove the determinant value is 0 only. Here also I am expanding the determinant by first row, plus minus plus 1 into, then minus 5 into, plus 2 into. So 1, leave this column and row. We have these 4 elements. I have to multiply 4 into 0, 3 into 0, 0 minus 0. The next one, 5, leave this column and row. We will be getting these 4 elements. 4 into 0, 7 into 0, 0 minus 0. Now last one, 2, leave this column and row. We are getting 3 into 0, 7 into 0, 0 minus 0. that is equal to 1 into 0 minus 5 into 0 plus 2 into 0, that is equal to 0, 0, 0, that is equal to 0. So, if any one of the rows or any one of the columns, all the entries are 0, then the determinant value is 0. That is given in that note. Next note is the determinant of a triangular matrix is obtained by its product of the principal diagonal elements. Give an example. Consider an upper triangular matrix. Because why it is called upper triangle? Below the main diagonal, if all the elements are 0, that is called upper triangular matrix. I am going to expand that determinant value. I am going to find out the value of determinant of A, that is equal to 271053004. We can expand along that R1 plus minus plus as usual 2 into minus 7 into plus 1 into 2 into minus 7 into plus 1 into. Here leave this column and row, we have these 4 elements, 5 4s are 20 minus 0. Next leave the second column and first row, we have 4 into 0 0 minus 0. Finally here leave this column and row, we have 0 0, 0 minus 0, that is equal to 2 into 20 minus 7 into 0 plus 1 into 0, that is equal to 2 into 20, 40 minus 0 plus 0, that is equal to 40. For finding this determinant value, you no need to expand the determinant. If it is a triangular matrix, according to that note, you just multiply the main diagonal elements. You will be getting the determinant value. Look at that. 2 5s are 10, 10 into 4, 40. Here it is. So again I tell you, if it is an upper triangular matrix or lower triangular matrix, for getting the determinant value, you just multiply the main diagonal elements only. Okay. Now property number 6, if each element in a row or column of a matrix is multiplied by a scalar k, then the determinant is multiplied by the same scalar k. I'll give an example. I'll give an example for property number 6. This example that I have taken in property number 2. The same example I have taken. You know that the determinant value is 10. I directly write here, that is equal to 10. You can refer property number 2. Property number 2 example. Okay. Now in property number 6, any one of the rows or any one of the columns is multiplied by the scalar k. Here I take k, that is equal to 5. I am going to multiply R1. R1 implies R1 into 5. R1 refers to row 1. I am multiplying R1 by 5. Therefore, we will be getting 1 into 5, 5, 5 into 2, 10, 3 into 5, that is 15. Second row and third row, write as it is. So, minus 1, 0, 1, 2, 1, 5. Now, I am going to expand the determinant, that is equal to, at the top you write plus minus plus, 5 into, minus 10 into, plus 15 into. So leave this column and row, we have these 4 elements, 0, minus 1, plus 1 becomes minus 1. Then second element is 10, leave this column and row, we have these 4 elements, minus 1 into 5, minus 5, plus 2 becomes minus 2, minus 5, minus 2. And leave the last column and first row, multiply these two, minus 1, minus 0. So 5 into minus 1 minus 10 into minus 7, 5 into minus 1 minus 10 into minus 7, finally 15 into minus 1 plus 15 into minus 1. That is equal to 5 into minus 1 minus 5 minus into minus plus 10 into 7 70 plus 15 into plus into minus minus 15 ones are 15, that is equal to minus 15 minus 5, that is minus 15 minus 5, that is minus 20, minus 20 plus 70, that is 50. See, here I multiplied the first row by 5, correct? I multiplied the first row by 5. I got the value of the determinant as 50. For that, you know the determinant value of the original one is 10. 10 into 5, that is 50. You can directly write. That is given in that property number 6. 10 into 5, what is the scalar here? 5. 5 into determinant value is 10. 5 into 10, that is equal to the same 50 here. Okay. So property number 6 is completed. Next note 7.9. If A is a square matrix of order n, then determinant of AB can be written as determinant of A into determinant of B. And if AB that is equal to 0, actually it's a O, the 0 matrix, then either determinant of A is 0 or determinant of B that is 0. So again I tell you, if the product of A and B is a 0 matrix is represented by the letter O, then either determinant of A is 0 or determinant of B is 0. And the third one, determinant of A power n, that is equal to determinant of A and whole power n. Property number 7. If each element of a row or column of a determinant is expressed as sum of 2 or more terms, then the whole determinant is expressed as sum of 2 or more determinants. I give an example. Here itself, look at that. This determinant can be written as, here the first column has the expression, so binomial, and second column and third column it's a monomial, single term only. This can be expressed as a sum of two determinants. In these two determinants, second column and third column are same. The first column of the first determinant is A1, A2, A3. And the second determinant first column is M1, M2, M3. That is given in property number 7. I will give an example, you can easily understand. We know that determinant value is 10 according to that example number, and property 2 of that example, here it is, property 2 example value, that is 10. I have taken the same example here. Now consider this one itself, you can write any format you can write. I am writing that is 1 plus 0. 2 we can write 5 minus 3 or 4 minus 2, like that. I write 4 minus 2. We need 2. Any format you can write addition or subtraction. 3 itself you can write 2 plus 1 or 3 minus 0 or 5 minus 2, like that you can write. Just I am changing that first row only, and second row and third row write as it is, minus 1, 0, 1, 2, 1, 5. Okay. So what I have done here, I have written that second row and third row as it is. So instead of 1, 2, 3, I have written 1 plus 0, 4 minus 2 and 2 plus 1. Value wise same only, 2 plus 1, 3, 4 minus 2, 2, 1 plus 0, that is equal to 1. This determinant can be written as the sum of two determinants. I write here Okay, listen. Here write that minus 1, 0, 1, 2, 1, 5. Here also minus 1, 0, 1, 2, 1, 5. That is common for both the determinants. No change at all. Here, look at the first element 1, 4, 2. Right over here 1, 4, 2. What's the second number here? 0, minus 2, 1. Right over here 0, minus 2, 1. Now I am going to expand both the determinants. Finally, you will be getting a same 10. We can check. That is given in property number 7. At the top you write plus minus plus. Here also write plus minus plus. Okay, now can expand 1 into minus 4 into plus 2 into. Okay, leave this column and row, you will be getting 0 plus 1 becomes minus 1. And minus 4 here, multiply these two, minus 5 plus 2 become minus 2, minus 5 minus 2, and the last column and first row eliminated. These 4 elements have to multiply minus 1, 0 for this, plus this part is over here 0 into minus plus 2 into and plus 1 into. Okay, for the 0, leave this column and row, you have 0 plus 1 becomes minus 1, then minus into minus plus 2, leave this column and row, we have 4 elements, 5 into minus 1 minus 5, right as it is, plus 2 becomes minus 2, minus 5 minus 2, and finally leave this column and row, we have these 4 elements, multiply minus 1 and 0. That is equal to 1 into 0 minus 1 minus 4 into minus 5 minus 2, that is equal to minus 7 plus 2 into minus 1 plus 0 into anything is 0, 0 into minus 1. Next step you can write 0 plus 2 into minus 5 minus 2, that is minus 7 plus 1 into minus 1 minus 0, that is minus 1. We have to simplify. 1 into minus 1 is minus 1, minus into minus plus 4 7s are 28. Plus 2 into minus 1 is minus 2, 0 into anything 0, plus 2 into minus 7 is minus 14, 1 into minus 1 is minus 1, that is equal to 28 minus 1, that is, first write 28, after that you can add the negative numbers, minus 1 minus 2, that is minus 3 minus 14, that is minus 17 minus 1, that is minus 18, 28 minus 18, that is equal to 10, same 10 here. So the value doesn't change. Okay, that is given in property number 7. So property number 8, very important property. If to each element of any row or column of a determinant, the equimultiples of the corresponding entries of one or more rows are added to or subtracted, then the value of the determinant remains unchanged. Same example I am considering what we have considered in property number 2. You know the value, that is 10. Now consider that R1 implies R1 plus R2 plus R3. In this determinant, I am adding R1, R2 and R3, I am writing in same R1. So look at that. So there is no change of R2 and R3. So better you write R2 and R3. R2 minus 1, 0, 1, minus 1, 0, 1 and R3, 2, 1, 5. No change at all. So R1 implies R1 plus R2 plus R3. Look at that. This is R1. R1 implies R1 plus R2 plus R3. That means add these 3 and write in R1. 1 minus 1, 2. 1 minus 1 plus 2. 2, 0, 1. 2, 0 and 1. Add these 3. 3, 1 and 5. That is equal to 1 minus 1, 0 plus 2, that is 2. 2 plus 0 plus 1, that is 3. 3 plus 1, 4, 4 plus 5, that is 9. And write the second row and third row as it is. Now I am going to expand the determinant. We will be getting the same value 10. We can verify. Plus minus plus, that is equal to 2 into, then minus 3 into, plus 9 into. So leave this column and row, will be getting 0 minus 1, okay, and minus 3, leave the second column and first row. You have the 4 elements. 5 into minus 1 minus 5, plus 2 becomes minus 2, minus 5 minus 2. Finally leave the last column and first row. We have these 4 elements, minus 1 and minus 0. That is equal to 2 into 0 minus 1 is minus 1, minus 3 into minus 5 minus 2, that is minus 7, plus 9 into minus 1 minus 0, that is minus 1. That is equal to 2 into minus 1 minus 2, minus into minus plus 3 7s are 21, plus into minus minus 9 1s are 9, that is equal to 21. Minus 2 minus 9 is minus 11, 21 minus 11, that is equal to 10. We got the same value 10. Okay. Here I have added 3 rows. Even you can add 2 rows. Even you can subtract 2 rows, 3 rows. So value doesn't change. The value of the determinant doesn't change. This is called the row transformation. Like that you can go for the column transformation. I can change column 1, column 2, column 3 like that. Okay. So it is given in property number 8. So far we have completed the properties of the determinants. So then I will be teaching that exercise 7.2 in the next video. Thank you, children.